This is Official Nerd Business. Hello nerd boys and girls and welcome back to our programming series. Today we will take a look at Euler problem number 19. We are counting Sundays. The problem statement, as you can see, I've already created my boilerplate with the problem statement copied in. We are concerned about dates, and the problem statement is apparently not quite copied. You are given the following information, but you might prefer to research for yourself. The first day in the year 1900 was a Monday. Here's a little rhyme about how many days each month has. And the description about leap years. So leap years is where February has 29 days instead of 28, and a leap year occurs on any year evenly divisible by 4, which you might have known, but not on a century, which you might not have known unless the century itself is divisible by 400, which I didn't know. How many Sundays fall on the first of the month during the 20th century? So mathematically this isn't very involved. It's a lot of counting, it's a lot of keeping track of where we are within this 100-year reach. And also note, this tricked me the first time around. The 20th century does not start at 1900 as given at the beginning of the problem statement. It starts in 1901 and it doesn't end at January 2000, but it ends at December 2000. So keep a very clear track of which dates we are considering here. So I've already I've got the boilerplate code. We can run this file on its own, and we can invoke this run method through our Euler running rig. And I've already implemented one attempt. Add a little comments here at the top because it's useful to know why these values have certain, why these variables are initialized to these specific values. So let's run through the attempt. What we are going to do here is bluntly counting the days in each month. We start at the given start date of January 1900. We aren't interested in Sundays in 1900 yet, but we'll get to that in a bit. But we do start there, and we simply add however many days this specific month has until we've run through all the months up to and including December 2000. And whenever we increase the number of days by with a month, we check if we've hit a Sunday at the start of the month and then add 1 to our total, which is the first variable here, total. It's also the last. And it's set to 0 at the start, of course. We start at a Monday, and there's several different ways in which you could look at weekdays. Sometimes it's good to start with the Sundays at the start of your week. Sometimes it's a Monday, sometimes it's a completely different day. And sometimes when you are counting things, weeks have 7 days. You can see each day as an element of the array week. And most arrays then have a 0 indexing. We simply want to continue counting days, and we start at 1, which is Monday, and we will see how that works in a bit. We keep track of the years separately, specifically for checking if this is a leap year or not. And months are 0 indexed into this array here, which also is stated specifically in the comment. So here is how many days we need to add for each month. So January has 31 days, March has, May has, etc. Basically it follows the rhyme up here, but this is basic knowledge, of course. And there is 28 for February, but we will get to February in a bit. And then there's the variable I, which we don't really use. It's only a loop counter. Specifically, we want to count off 100 years plus 1900 itself, and we want to look at each month in those years. So this sets up the limit for the loop counter, and this increments the loop counter. So this makes sure that we run over all of the months we want. Now, as soon as we start with processing a month, we check if our d variable modulo 7 is 0. And what does the modulo operation do? It checks to see if a division leaves a remainder. So if we have 15 modulo 7, then of course 15 divided by 7 is 2. 2 times 7 equals 14. Then the remainder of this division is 1. So 15 modulo 7 will produce 1 as a value. If we started this calculation with 14, then we would have 2 here, and this would also come back to 14. 14 minus 14 is 0. So the modulo values of 7 are 1 for 1, for 8, for 15, for etc. 2 for 2, and for 9, and for etc. again. 3, 4, 5, 6, and then 0. So if we were to plug in 1, we would get a 1 back. If we plug in 2, etc. until we plug a 7 in, we would get a 0 back. Now we plug an 8 in and we get the 1 again. We plug a 9 in and we get the 2 again, and we get the etc. So that's how modulo works for those that haven't seen this operation before. And we take advantage of it in this case because we keep adding days to this day counter. So we are not concerned with a year having only 365 days. We simply keep on adding. So all of the days in these 101 years get added to this. And whenever that hits a clean 7, we add 1 to our total. Second condition here is that we are in the second year of counting because we start at 1900. But the problem definition says we are not interested in 1900, we are interested in 1901 and above. So that's what this does. Then I want to take this entire if behemoth upside down and start here. To increment the number of days that we have had, we start at January 1st, and to see what February 1st is, we need to add 31 days to our day counter. So that's what this bit of code does. It takes the number of days we had, it looks up in the adds array above how many days this specific month has, adds them to it, and then continues on. Now, we do have a month counter, so that starts at January at 0, and then February, which is a special case, then March, etc. If this hits 11, which is December, it sets the month counter itself to -1, and then immediately increases it again to 0, indicating January. So this is your year rollover, and whenever we do roll over a year, we add 1 to our year total. Now the year total is used in this specific bit of code. So if we do hit February, which is at position 1 in our array, then we check the year. If the year is a century but it is divisible by 400, then we do have a leap year and we want to increase with 29 days. If it is a century but it isn't divisible by 400, we don't get a leap year. If it is divisible by 4, or modulo 4 if you will, leaves no remainder, then we do have a leap year, and in every other case we don't have a leap year. So that's what's happening here for February. So basically this just keeps track of, we've seen 31 days, we started out at a Monday, at what day are we now? Is it a Sunday? No, it isn't. Now we've seen 60 days, we started out at Monday, is this cleanly divisible by etc, etc. So basically we're just counting them off and then returning the total. Does that work? Is this sufficient? Well, let's see. If we run program 19, we do not need to specify a parameter. Then we get a 171, which I can tell you, spoiler alert, is the correct answer. If you enter this over at Project Euler for problem number 19, you will get the green check. It took us virtually no time whatsoever because it's only like 1200 very small calculations or loops over 3 calculations. So it's, for modern processors, it's absolutely nothing in the way of load. So it runs pretty quickly. But you might wonder, is there another way in which we can do this? And in fact there are several. Since we are talking about dates, I'd like to show you a way to do this with the built-in date functionality of Python. And for that I need to import datetime. So we will need a variable called d, or well, we can call it anything we'd like, but d will be a datetime.date object, and when we create it, it needs a year. Once again, we start at 19. In this case, we can start at 1901. We start at month number 1 and we start at day number 1. So this describes the first date in our in the range that specified in the problem. And then we can simply say the date as a year property. And while it isn't 2001, we want to continue on our loop. Once again, we do need a total variable, which we will set at 0. And now we need to increment the date. Now, dates in Python don't have a simple add method to add a number of days or months or a given interval. We have the time delta object for that. So the datetime module comes with a time delta. However, this takes a specific parameter to define how many milliseconds or how many days or how many seconds or minutes this spans. Unfortunately, there isn't a month's value here because every other value you see here, so the days or the seconds or the milliseconds or even the weeks, all have a given certain amount of time in them. A week is 7 whole days, never more, never less. Months are very sketchy in that respect, and that's something that they don't support with the default library. There are external libraries that do better support date functionality, but we are working with the standard here, and there are ways to get around that. We can simply get the year and month values from our current date. Now note how we specify these by having 2 values and a comma on the left hand side of the assignment. We can also specify 2 functions or values, or in this case properties, to be assigned to those 2 values on the left hand side in that specific order. This is fun if you have lists which you can expand with the asterisk to be assigned to separate values on that side. For now this will work just fine. Let's see if the month value currently is 12, then we want the year value to increase by 1 and the month value to be set to 1. Else we simply want to increase the month value, and then we set D to be a new date. So this is how we increment the date. Or in fact we don't increment the date itself, we simply use some homebrew logic to see if we can increment the month value of it and roll over the years when necessary. and then we instantiate a new date based on this specific pattern. Now for the magic bit, here we go. There is a weekday function, and if this is 6, we are looking at a Sunday. So in that case we want to add 1 to our total, and if it isn't a 6, then we don't want to add anything to our total. Could have reversed this, could have started with the if, whatever. So this should once again give us the correct answer. Based on dates, not based on bluntly counting how many. So in fact we are, by doing this, we are skipping the whole February mess. Let's see now. Let's run attempt number 2. In fact, 2. Let's run this file. Why not? Again, 171. So this is we get the same answer, but this time it's based on the actual date functionality that's included in Python. Instead of keeping track of the February mess ourselves. But both are viable options in this specific case. In fact, there is a third method which I want to show you, which is a happy coincidence that it works in this case, but while we're at it, let's show it anyway. Basically what we could say, this is a bit of a one-liner, what are the odds of any given day being a Sunday? Well, there's 7 days a week and only one of them is a Sunday, so in any given week the chances of you hitting a Sunday is 1 in 7, right? And any given day in a year needs to be one of 7 values, one of which being Sundays. So each day has a chance of 1 in 7 of being a Sunday. And we are looking at 12 days a year, and we are looking at 100 years in our century. And this will give us a decimal value, so this will too. But we can solve that by dividing everything, integer dividing everything by 1, dropping the decimal part. Now this is a bit cheaty, really, but lo and behold, we do get the correct answer. This is a happy coincidence. You might very well have a century or any range of years. The century is big enough for this to work. That's basically the bottom line. You need a big enough n to equal out any weird edge cases. So it's a bit cheaty, but it works. So it counts. So yeah, that's problem 19. We've looked at bluntly counting things. Not terribly mathematical, but in coding practices you will occasionally see these type of branching ifs, so it's good that we've seen that on a learning how to program side. But when working with dates, your gut instinct should be, let's see if my platform has a default date format and how can we use that. And in this case, since we are looking at math, probability here shows that we also get to the same answer as we do with blindly counting. So that said, I hope to see you again for problem number 20. Once again, don't forget to like, subscribe and check out my GitHub where all of the source code is stored. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.